So back to circuits. So simpler than trying to figure out whether we're for or against the NFL. Impartial. Okay, so the series, we're going to start with the series RLC circuit. That's the only one that we're really going to be tested on. There is also a parallel one, but this is mostly an introduction. So if you get really interested in this, take a circuits class. Okay, but you can sort of figure out what happens in all other configurations because you just use the tools that we've already been given, like loop and junction law, and you can look at how this is going to behave as you change the structure. You just use Ohm's law, but now you use Ohm's law with reactance. Wake up. Okay, so series RLC circuit. All right, here is our voltage source. Guess what the R stands for? Yeah, it does say it. Okay. And L is for inductor, because L is for inductor. This is like a terrible way to teach your children the alphabet. Okay. And C is for capacitor. The cow says meow. All right. But remember, in a series circuit, what is the same through everything? Current. Okay. So the instantaneous currents should be the same through everything in your circuit because it's a series circuit. And that's why we start with the series circuit. You have this one thing you can be sure about, which is that the instantaneous currents are the same. And the instantaneous voltages, remember these are lowercase b's, should add up, right? This is loop law. So at any given time, if you take the voltage across this, and 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 add them together, what should you get? Don't look at that. If you go around a loop and you add up all the voltages, what should you get? Zero. Okay? So this is just junction law. This is loop law. Okay? What do they call them in electrical engineering? It's like, okay, nobody knows.
Drew would know.
I guess you guys haven't taken it because this is the prerequisite to the circuits class. So.
For what?
I think there's like mesh and node analysis,
Yeah.
but it's like the same as loop and junction law. They have like more techniques they use. Leave her alone. She has to take it. Okay, so that's how this is all still true. But remember, these are just the instantaneous values, not the peak values. Because what do we know about the peak values? Do they follow loop and junction? Not necessarily, okay? Because remember, they all peak at different times. So this one's in phase with this, and these two are out of phase with this by pi over 2, one direction or the other direction, okay? So, because it's a pain in the ass to draw a bunch of sine waves, let's look at this in phase space. So we'll do the phasor analysis, okay? And let's start with the phasor we know is the same for all of them, which is that. Current. Current should be the same for all of them, okay? So we'll start with current. And we'll just pick a random angle because, remember, the angle omega t is always to what vector? What determines the frequency? Let's go back. What determines the frequency?
Current. Everybody just guess. It'll be fucking easier. Just throw something out.
Okay, forget everything we were talking about. Why do you have a frequency? The power source. Okay, this is an AC source. So this omega t angle in phase space always goes with this. Okay, it's always to find this because this is the thing that drives the whole circuit. Now what you'll notice is we're kind of doing this backwards because what we're looking for is that. Okay? But you can go either way. This is just a technique for finding these things. So we start with current because we know that's the same for everything. Okay? Where do we put the voltage across the resistor? Where do we put that phasor?
90 degrees. No, it'll be the same.
It'll be the same as current. Why?
Because the resistor and the current don't have a phase difference.
The resistor does not introduce a phase difference, right? Remember, current and voltage are in phase for a resistor in an AC circuit. That was a good job. Okay, so A plus for this thing that only kind of matters. But this is the phasor for voltage across the resistor. Okay, where does the voltage across the capacitor hang out? 90 degrees this way. Okay, so voltage across the capacitor lags behind the current. Well, current leads the capacitor voltage is how we said it before. So the voltage of the capacitor is over here. Where's the voltage for the inductor?
Oh.
Yeah, the other way. Okay, so here's our inductor voltage, capacitor voltage, resistor voltage. Okay, how do these things add up? Remember, these are all the peak voltages. If we want to know the instantaneous voltages, how do we find those? You project them onto the x-axis. So this would be the instantaneous voltage for across the capacitor. This would be the instantaneous voltage across the resistor. This would be the instantaneous voltage across the inductor. You can see they're all peaking at different times. And peaking means they cross the x-axis, okay, because that's when you get the maximum voltage. So how are we going to find our source voltage from all this stuff? Add them up, but add them how? Just the numbers?
Vectors?
The resultant vector, okay? So the resultant vector should be the sum of all of these things. And how do you add up these vectors? Well, yeah, you can add them tip to tip. That's true, actually. But what's nice about these is they're parallel. So you can just subtract this one off of this one. And then, to add it to this one, what do? Now you have two perpendicular vectors. Right triangle. How do you find Pythagorean theorem? Okay, you learned it in what, 4th grade, and it's still useful. So it is, because we're going to use it right now. So here's your Pythagorean theorem. Here's your hypotenuse, which is epsilon naught. That's your voltage source, right? That's your voltage source maximum value. Here's the voltage of your resistor, and these go together because they're parallel, so you can subtract them first, and then whatever these give you when you subtract them, because they're parallel, is the other leg of the triangle, okay? Omega t is going to be from cosine omega t, so you can figure that out. You'll see. So here, you can add them this way, and here is your epsilon naught. That means this is omega t, okay? So you can see when you add these up, you get epsilon naught, and you can see how things respond relative to your voltage source. Now that's what's tricky in the RLC circuit, because this is what you put in, even though we found it last, okay? So that means if this is relative to this, the angle between here and here, that's not omega t, that's not pi over 2, it's not 0. There's an angle here, okay? And the relationship between the current through the circuit and the voltage source has an angle, has a phase difference. And that's what we're really worried about, because that's how you know how your circuit's operating. And we'll talk about what that means in a second. But this is called the phase angle. And that's the angle between your voltage source, okay, which is what drives your circuit, so it's pretty important, and the current you end up getting. And you can measure this current across any of the circuit elements because, remember, your current through a series circuit should be the same everywhere, all right? So this is your phase angle. How are we going to figure out what this angle is?
Inverse, cosine, or
Inverse tangent, right? Because we know if this is a right triangle, this would be one leg of the right triangle, this would be the other leg of the right triangle, okay? So you can take tangent inverse of these things, yes?
If the angle's between epsilon naught and VR, why wouldn't you use the tangent from those two vectors?
Or between epsilon naught and you can.
Create that.
I know, but you just pointed to VL minus VC as the tangent.
Well, this would be cosine, right? You can do cosine inverse
Okay,
of,
so-
but it depends on what information you have. And so if you're using phase space, all of those things are valid ways to do it. In general, okay, if you want to find tangent phi, it's what over what? Opposite over hypotenuse, so that's VL minus VC over VR. Okay? What do we know about?
Yeah, why is it hypotenuse with tangent?
That's not. I messed up. But she repeated that.
Wait,
It's
what?
opposite over adjacent.
Oh.
EMF is your.
Well,
So-
I did opposite over.
EMF is
I
your.
said out loud over hypotenuse. and you're-
Oh, sorry, because I just repeat stuff. So, but I wrote the right thing, so look at the thing on the board. This is what it is. But one more thing to remember, all of these things, these are all the peak voltages, okay? We could still use Ohm's law, which means that everything is V is equal to I X, okay? What do we know about this for everything?
Just train it.
It's the same. So you can simplify this to also XL minus XC over R, okay? Which might be useful sometimes. But generally you're just dividing top and bottom by I because we know it's a series circuit, okay? And this, of course, is omega L. This is 1 over omega C. There you go. Okay, so we can figure out phi using this. And so we can add the instantaneous values of the voltage to get to 0. But if we want to add the peak values, remember, they have to be squared like this. Okay. And so the equation for current is just I cosine omega t minus phi. This is the phase angle that we're calculating there. Okay? What this says is we can solve for current. There's some algebra that happens, but it looks essentially like this. This is still just V equals I times reactance. And remember, this is a series circuit, so you're just adding up the different reactances, essentially. Okay, but you have to add, if you're adding up the reactances, it's not as simple as just adding them. You have to use this. Okay, so you solve for the equivalent reactance by using sort of your Ohm's law starting here. Okay, so we're just trying to figure out, and the main thing is, look, if these are all V, you can pull out the reactance and the current and separate them out. Okay, and that's how we get this. Okay, so just looking at this, how does this respond? What happens when omega gets really big?
Current gets small.
Yeah, the current should get small, right? When omega gets really big, what happens to this thing, this term?
Zero.
That should approach 0. But what happens to this term? It should get pretty big, okay? So the current doesn't go all the way to 0, but it gets relatively small, all right? What happens when omega is very small?
The reactance is big.
Actually the same thing, right? So when this is really small, this term gets really small, this term gets really big. So it's small. If it's large, it's small. If it's small, when is it big? Well, you want to try it out? How do you maximize something? Yep. Okay. So how are you going to maximize current here? Take a derivative. Jumble. All right. Well, if you guys aren't going to try to do this, then I'm not going to either. So it looks something like this.
Yeah,
All
alright.
All right. So you have to do chain rule. You can see you have to pull this thing up. So you guys have taken calculus allegedly.
Taken.
Anyway, it ends up being relatively simple because you set this equal to 0, so everything in the denominator is fucking useless, and then you just have to worry about the numerator, and the numerator just has 2 terms, and you just set them both equal to 0 and solve, okay? What that gives you is 0 equals this, which gives you omega is equal to 1 over the square root of LC, which is pretty simple, okay? What is this kind of, what is it when you have one frequency that's special? What do you usually call that? That is a resonant frequency. And anybody who's ever blown over a bottle of, like a Coke bottle or a water bottle and made a tone is familiar with resonant frequency. Or if you get the like wine glass and you move your finger around it and it hums, right? That's resonant frequency. Or if you build a bridge and it collapses in a wind, that's also resonant frequency. And so if you're a mechanical engineer or an electrical engineer or lots of kinds of engineer, you should be really concerned with resonant frequency because physical objects have a resonant frequency, like a wine glass, and if you match their resonant frequency, they'll start oscillating a lot. And if they oscillate a lot, that means they're moving a lot. And if they're moving a lot, you can get them to move so much that they break, okay? And that's what happens with like the Tacoma Narrows Bridge, right? The frequency of the wind going past it matched the resonant frequency of the bridge starts swaying. The wind blows, it sways more because it's hit resonance, and then it falls apart into the river, okay? If you build a pier, piers have a resonant frequency. You want to make sure that resonant frequency is not going to be in any way similar to the frequency that waves come in and hit the pier, okay? So when you're building things, you have to worry about resonant frequency, right? When you're dealing with things like circuits, you have to deal with resonant frequency because guess what? That's how radios work. You send out a frequency, you can tune your radio on the other end to that same frequency. Now you're receiving the signal because they're resonating, okay? This was sort of like the idea behind how Tesla thought we could give everybody free power through the air, okay? But essentially, what does the graph of this look like? Well, remember, we know if omega is small, what happens to the current? Small. If omega is big, what happens to the current? It's also small. So the only time you have a big current is when you get close to this, which is the resonant frequency, which depends on what? What's L? The inductance in what units? Henries. This is the capacitance in farads, okay? So you pick your inductor and capacitor, now you have a resonant frequency. What does this not depend on that's also in the circuit? The resistor, okay? There is no R here. The R vanished when we took the derivative and solved for omega, and it does come up somewhere, okay? It comes up in the height of your peak, okay? You can see bigger resistance, smaller peak current, which should make sense if you remember V equals IR, right? Bigger resistance always means smaller current. So the maximum current is just going to depend on R, because if you look back over here, all right, if omega is equal to 1 over square root of LC and you plug it in, this term goes away at resonant frequency, which means this reduces to D is equal to I square root of R squared is R, because this whole term becomes 0. So the peak current just behaves with V equals IR. So obviously if you have a bigger R, you have a smaller I because the voltage is always the same, okay? So here's our graph of resonant frequency, and the maximum current is always the voltage divided by the resistance, the peak voltage divided by the resistance, okay? So this is your resonant frequency, and that means you have a resonant frequency. I don't know, what other conclusions can we draw here? Any questions about that?
How do you count the frequency of a bridge?
There's
so many different materials. Like, do you find each individual one and then
magic.
That's a good question.
Or do individually look at the stone and the metal and see which will break first? Like,
I think you actually usually run a simulation by putting in all the materials. But I can ask my dad because he was talking about, so like for instance, at the port of Portland, right? When they switched from so before big shipping containers, right? People would just load stuff onto ships, which was less efficient, obviously. Now they have big shipping containers, but what do you need to move shipping containers around? Giant cranes. See, they added a bunch of these cranes to the pier. They're all anchored to the pier. Guess what? That changes the resonant frequency. So when they did a structural assessment of the new pier, they had to recalculate the resonant frequency and make sure it wasn't bad.
was it?
It wasn't, but I don't know how they did that, so that's a good question. That's an engineering question. So I will ask an engineer. Because it seems like there's like some protocol for doing that I never learned because, you know. Okay. So here's a question. All right, let's discuss. At least we know it doesn't fluctuate wildly. Better. Okay, so what do we know about the resonant frequency? What does it depend on? L and C, right? Resonant frequency is going to be 1 over LC. So if you change R, does that change the frequency at which this thing resonates? No. What does it change? The maximum current, okay? So it changes the peak size, but it doesn't move the peak left or right. So it doesn't increase, it doesn't decrease, it stays the same, okay? All right, next question. It's a wide range of answers. Okay, please. Better. So it's going to be C over 4 because we have the capacitor in the denominator, so it has to be divided, so it ends up as something in the numerator. Okay, it's a square root, so 2 would give you square root of 2 in the numerator. 4 gives you 2 in the numerator. So if we want to double it, we have to divide C by 4. Okay. Okay. So if this is what you have, right? If this is the current and your voltage from your source, remember, are these things in phase? No. So the voltage here would be green. You can see its peaks at epsilon naught. The current's going to be purple. So this means we are below our resonant frequency. That means X sub L, our inductive reactance, is less than our capacitive reactance, because remember this X minus L depends, it really has an impact on the phase because you're subtracting them. So one of these will give, if this is bigger, it gives you a negative value. If this is bigger, it gives you a positive value, okay? So that has a big impact on your resonance. And that means your phase is less than 0, okay? And the current leads the voltage, all right? If you're at resonance, okay, that means these two things are equal. Because your phase difference, if you want this angle to be 0, these have to give you 0, okay? So that means your X sub L and X sub C are equal. That means your phase is 0 and you're on resonance. This will give you your maximum current. It'll be a much larger current when you're at resonance, okay? Here you could be above resonance. That means omega is greater than your resonant frequency. X sub L is greater than X sub C, and that means angle phi, which is the phase between voltage and current, is going to be greater than 0. That means current lags voltage, okay? Now how is this significant? Well, if you have something like an AC generator, what do you want your phase to be? What kind of current do you want? You probably want to maximize your current. So you want to design motors, you want to design generators so that you are on resonance, okay? Which means you have to pick your inductor and capacitor wisely to go with your frequency, okay? depending on what your applications are. That's a very abstract way of saying it, but whatever you're building, you want to be aware of this resonance, because remember, power is I times V, current times voltage. But remember, in this case, it should be instantaneous current times instantaneous voltage. And if you use your V equals IR stuff, you end up with something that looks like this, okay? So the average power is going to be the total energy dissipated per second. That looks like this. And this 1/2, which we didn't have before, comes from what? Oh yeah, the fact this is AC, okay? These are peaks, and so you have to actually find the average power, okay? And the average power of a graph that looks like this is here. So if this is your peak, right, I squared R, then your average should be at about half that, okay? So we're always dealing with average power because the power fluctuates just because the voltage source fluctuates. And this leads us to something called root mean square, okay? And what you'll notice here is you have a 1/2, yeah, it ends up being square rooted, basically, okay? And the reason we learn this is because this is how you use the same math we used in DC with AC stuff, okay? So the root mean square current and voltage just look like this, okay? It's the peak voltage divided by square root of 2. Now the reason it looks like this is because it's supposed to give you the right power, because your average power is half your peak power. If you look back over here, okay? Your average power, here's your peak power. Your average power, this thing that we're trying to deal with, okay, that works the best for calculating power, that's going to be half of your peak power. If you have to multiply current times voltage and you want to get 1/2, you just give them each 1 over square root of 2, because 1 over square root of 2 times 1 over square root of 2 is 1/2. Okay, so this is just kind of a hack to get that answer. Okay? Oops. Oh, why is that there? All right. So what you do, so basically this gives you regular power. So you can treat it like DC. Power is just current times voltage. Now when you multiply current times voltage, you get 1/2 the peak power. Okay? So the RMS current is just 1 over square root 2 of the peak current. And the RMS voltage is just 1 over square root 2 of the peak voltage. This is a shortcut people do so they can make calculations in the field without having to do a lot of extra math. You just use the DC math, and all you have to do is add this nice factor. It gives you 1/2. All right? So then you can treat power the same way we did for DC. It's just I squared R, but I is RMS current, okay? It's V squared over R, but V is RMS current, and this is I times V, but they're RMS. And what you'll notice is that's just the peak current, right? And it introduces a 1/2. This is the peak. If you use the peak voltage, it introduces the proper 1/2. If you use these, it also introduces 1/2. So it's always giving you the average power instead of the peak power, which is what you would get if you just use the peak current and voltage. Okay? So the average power supplied by the EMF, that's just current times voltage. Okay? But you use the RMS one because now it works just the same as DC. You don't have to learn new formulas. Okay? So, for instance, the power rating on the light bulb is actually its average power, which would be 120 volts, root mean squared. Okay? So, let's try out a whole thing. Okay, guys. So, what's the resistance? Well, turns out 120 volts is peak or RMS voltage?
Average.
That's the not average. RMS is not average. It's like a sort of average, okay? It's like the square root of the average, because the average would just be half, right? So it's set up so that you get the average power, because power is the thing that we care the most about, all right? So our resistance is just going to be VRMS squared over power, just because we have power is V squared over R, okay? This is like back to the, and this is the average power, this is the average power, and this is RMS, right? So we're plugging this in. This is 120 volts squared over 100 watts. What does that give you? That would be 144 ohms. Okay. Then we can use P is equal to I RMS times V RMS. So the current RMS is equal to P over V RMS, which is 100 watts over 120 volts, which is 0.83 amps-ish, okay? And what current is that? That's the RMS current. We want the peak or max current, okay? So how do we go back and forth between RMS and peak? Well, I RMS is equal to square root of I peak. So if we want I peak, we just take I RMS and divide by square root of 2, and that's going to be 0.83 amps divided by square root of 2, which gives you 1.18 amps, okay? So RMS is not quite the average. It's like the square root of, it's just the root mean squared. It's hard to really describe, but it's set up to give you average power so that all of your power equations are the same as DC, which makes life easier in some ways and much more complicated in other ways. Mathematically easy, conceptually annoying. Yes?
I think you got those switched around.
Yeah.
Simplification.
Times square root of 2. Oh, because this is, sorry. So, yeah. But the answer's right. Okay. It gets bigger, is the idea. Because the peak current should be bigger than the root mean square current, which is how you check to make sure if your answer makes sense. Okay. Ooh. We got a couple slides. We'll just finish this off. So here, look, we have our capacitor voltage. This is something we're already familiar with, okay? In an AC circuit, the capacitor oscillates with source, okay? So energy flows in and out of the capacitor. The capacitor is charged and discharged. The energy isn't really dissipated like in a resistor. The energy just gets stored as potential energy and then released as electrical energy. Okay, so if you want to look at the power for a capacitor, it looks like this. This is the instantaneous power flowing in and out of a capacitor, which means instantaneous power is voltage times instantaneous current. And you get this whole thing, right? So you plug in the voltage sine wave, you plug in the current as a sine, okay? You do some trig stuff, and you get something that looks like this, okay? Because this times this gives you this factor of 1/2. That's a trig identity. Everybody loves those. And we end up with something that looks like, well, it's also a sine function, but it's twice this, okay? The whole point is the energy gets stored and it oscillates just like the AC circuit, okay? When we're talking about any kind of RLC circuit, we have this phase difference that's introduced by this phasor analysis that we did. So we can always find the phase difference between the current and the voltage. So if you multiply peak current times peak voltage to get power, you end up with something that looks like this. This is ignore, this isn't the average anymore. We're actually including the sinusoidal features of this wave, okay? And what I really want you to look at is, what does this cosine phi do to your equation? When is it maximum? What phi gives you a maximum power? 0, okay? So you want to be on resonance to get your maximum power. This is already what we were saying, but this is the math behind it. So this is called the power factor, and it arises if the current and voltage are not in phase, which means you're not on resonance, okay? So whenever you design a large industrial motor, you want to set it up so the power factor is as close to 1 as possible, because that's the maximum efficiency. It's not always possible to do that, but you want to get it as close as you can to resonance. Okay, so resonance does have an impact in actual design of electronics, of motors, and of generators. All right, that's the end of that chapter.